Alright everyone, welcome back to Algebra 2 Semester 2. We're on the last legs of the semester. Skill 22, probability of multiple events. So last time we talked about basic probability rules where, you've got some event happening and it's got chance from 0 to 1, which represents 0 to 100% chance of happening. But what if you want to talk about two different events, an event A and an event B? Well, we can usually describe them using the words and or. And today we're going to talk about those terms, okay, and how they relate to your events, okay. And we're going to use some Venn diagrams to help because that typically helps us visualize, and I think it's very helpful to really get that into our head about what happens when you have two separate events, okay, and how they interact with each other, their probabilities. So let's go ahead and get started. First of all, we have the and relationship. If you want both A and B to happen, okay, usually, let me go ahead and get a circle out here. Okay, let's call this circle. We'll call that circle A. And for the second circle, I'm going to make it a different color, just so we have that. I'm going to move it here, so I have a little bit more overlap. We're going to call this circle B. So if A represents the chance, okay, the event A, and B represents the event B, okay, with any point inside representing a chance that it happens, then A and B, okay, is represented by this area right here in the middle. Well, of course, that kind of makes sense, right? If you think about it, okay, if, let's say, you are riding a bicycle, and that's event A. Well, okay, I could ride a bicycle anywhere in that circle A. And let's say B is using your phone, which you shouldn't, okay, but let's say you're using your phone while you're riding your bicycle. Okay? Well, if you're doing both of those things at the same time, then you'd be in this area, right? But if you're just using your phone or you're just riding your bike, you'd be in one or the other. So when you say A and B, that event is described by the intersection between two events. Intersection. All right, let's go ahead and continue onwards. I'm going to be using the same colors for my circles on the other ones, A and B. Okay, but I'm not going to be rewriting the letters there. You're just going to have to remember which ones they are. So for A or B, so that means I could be riding my bike or using my phone. Well, as long as I'm doing one or the other, it doesn't really matter whether I'm in one or the other or both, because that would technically mean I am riding my bike, okay, right? I could be riding my bike, or I could be using my phone, or I could be doing both. So that little middle section is still highlighted, okay? But essentially, if you've got an or statement, you're essentially occupying any space where A and B occur, okay? So here's A, here's B, and if I'm doing A or B, then I'm in all, I could be anywhere inside here. And so I highlight the whole thing. That whole thing is fair game. All right, let me scroll down here. And it's going to move my graphs along with it, so I'll have to move it along. There we go. Okay, so lastly we have not A. Not A. So let's just take it as a simple event with no B. First of all. Well, typically, okay, we represent the sample space, which would be your however much 100% is, by a box, okay, where this circle represents A, the event A, but this out here represents not A. Okay, so anywhere outside in the box, okay, but not inside the circle, represents not A. That's if you're talking single event, right? So I'm talking about outside the circle. And these for the upper examples, you can kind of imagine a box encompassing A and B, and then being shaded outside would be your not A. But how about if you have two events? Well, let's take a look. You got A. Change my color here. We got B. Excuse me. right? And we got our big old box representing the whole sample space. Okay. If you want to talk about a not A for this one, well, here's A, remember? And anywhere outside this circle is not A, okay? Which means you'd be highlighting all this stuff outside in the box, right? Which is totally fine. But not only that, you're alright to be in B as long as you're not also in A. So this part also gets shaded in. It's treated as if it's not there in the first place. Okay? So not A, you simply can't shade inside whatever event you're talking about. Again, back to the bike and phone example. Let's say you are not riding your bike. Well, you just can't be inside the circle A, right? You don't qualify as part of that group, okay, of people who are riding their bike. But you could be using your phone. That doesn't really matter. Or you could not be. Well, that doesn't matter either, as long as you're not riding the bike, right? All right, so make sure to copy these down. These are very important, okay? And I'm sure, okay, you might have some questions depending on how well you understand the Venn diagrams here, but I think it is fairly straightforward if you think about them not as a probability events, okay, but as different categories, okay, different categories. Okay, now let's talk about dependent versus independent events. Let me clear my board here and scroll down. Okay, so when we talk about probability, there are these things called dependent and independent events. Okay, and it's actually pretty simple. Okay, but a dependent event, okay, a dependent event is an event in which one affects the outcome of another. So instead of an event, I should probably say two events, because we're talking about two events anyway. Excuse me there. All right. So pretty self-explanatory. If they depend on each other, then obviously they have to be affecting each other in some way. So that's how we call that dependent events. Independent events, on the other hand, okay, are the opposite. One event occurring has no effect on the other. Okay. So I guess I should have, moved this over a little bit. Okay. So one event happening has no effect on the other. So independent versus dependent. This is kind of difficult to realize, but let's take a look at the examples to see what I'm talking about here, see what Mr. Who's talking about. Are the outcomes of each trial dependent or independent events? Well, if you roll a die and spin a spinner, are those two tools related in any way? If I roll a die, well, you got a 1 out of 6 chance, right, to roll any number, okay? Does that affect my chance at spinning the spinner? I don't think so. All right, I don't think so. These are independent because neither of them affect the other. Okay, neither of them affect the other, right? Those things are not related at all, okay? If you roll dice and spin a spinner, you wouldn't expect one event to affect the other. So those are independent events. That, of course, would mean the second one are dependent, right? Pick a flashcard, then another from a stack of 30 flashcards. Well, if you picked one flashcard, you no longer have 30 flashcards, right? So the chance that you pick a different card has changed once you take that one card out. Dependent. Number of cards changes after picking the first. Okay, so that's kind of the separation, the distinction between independent and dependent. I think it's pretty simple. Okay, but in future, like when you go to higher probability classes or you talk about more complicated things, these can be a little iffy. Okay, but really we're going to focus on the independent nature of events for now, and we might talk about the dependent stuff later. Okay, but for now let's talk about independent events. Let me clear my board again. Sorry about that, a bit of a glitch there. But back to this independent events idea. Okay, why can I not type? Hello? Okay, here we go. If A and B are independent events. So they have to be independent, first of all. Okay. Then the probability of A and, whoops, I forgot my parentheses. A and B is the probability of A times the probability of B. And it's really that simple. Okay. So if you've got two independent events, okay, and you've got a chance, you know the chance of each thing happening, then to get the total combined chance of both happening, you just multiply the two things together. Very simple rule. Okay. It should make logical sense. If I roll a die, there's like a 1 out of 6 chance of rolling a 1 through 6. And if I roll it again, well, it's a 1 through 6 chance, a 1 out of 6 chance of rolling it again. So if I wanted one number followed by another number specifically, it's 1/6 times 1/6. Okay, let's take a look at the example. Okay, there are 10 diet drinks and 5 regular drinks at a picnic. There are also 8 bags of fat-free chips and 12 bags of regular chips. If you grab a drink and a bag of chips without looking, what's the probability that you get a diet drink and fat-free chips? There should be more space here, but I'm going to be doing it out here just for you guys. All right, there should be more space to do that work, but I guess I forgot to put it there. Okay, so first of all, let's take a look at our drink space. 10 diet drinks and 5 regular drinks for a total of 15 drinks. Okay, here's my diets, here's my regulars. And then I also have 8 fat-free chips and 12 regular chips. So fat-free, and here's the regular chips again. So here's a total of 20 chips. Okay, 20 chips. Okay, so I'm looking at diet drink fat-free chips. Okay, so diet drink, I'm going to change my color here. Here's that, and fat-free chips. All right, here we go. So when I look at what my numbers should be, it should be 10 out of 15 chance to pick a diet drink, and 8 out of 20 chance for fat-free chips. And if I want the combined, okay, probability of both things happening, you would simply multiply these together. Simply multiply those things together. 10 times 8 is 80. 15 times 20, well, that's like 300-ish. Okay, and so this would be your answer. Of course, you want to make it a little nicer looking. Maybe you want to simplify it a little bit. This should actually be 4 over 15, okay, which you can get by dividing both sides by 20, right? Or you could just do this cross multiplication thing, cross canceling, that kind of stuff. But this is the probability at the end. If you want to change it to a decimal and then percent, that's fine. But you can honestly leave it as a fraction. It's something that most probability statisticians do. They just leave it, like that. Okay, moving on. We've got mutually exclusive events. This is a pretty long lesson, so it might be a little longer, all right, of a video. Pause if you need to take a break or anything like that. But let's talk about mutually exclusive events. Okay, this is when you have two events that cannot happen at the same time. They are mutually exclusive. You may have heard the term mutually exclusive. It means you can't be both at the same time. Let's say, for me example, I can't be asleep and awake at the same time. Those are two mutually exclusive events. I mean, typically anyway. There's always that little half-conscious state when you are waking up, but technically you're awake. So those two things are things that can happen. I could be eating or drinking. I can't do both at the same time. Usually that's how that works as well. Okay. Or like my glasses are on, glasses are off, kind of deal. Those things, are some examples of mutually exclusive events. With the middle stage is not including, but let's say those are things that have to be separated, right? So let's take a look at our example. You roll a standard die. Are the events mutually exclusive, and explain? Alrighty. So here we get to our example. If you want to roll a 2 and a 3 at the same time, could you do it? Well, your intuition would say no, you can't, because I can only land on one or the other. I can't do both. Okay, so not possible in the same event. Okay, the one dice roll. So these are mutually exclusive. All right. However, the second one, rolling an even number and a multiple of 3. It should be even, not event. Even number and a multiple of 3. Well, what are my even numbers? 2, 4, and 6. What are my multiples of 3? 3 and 6. Well, look at that. We've got a bit of overlap between the two groups of events. And when you see that overlap, okay, when you see that overlap, you know, okay, based on that these are not mutually exclusive. I'm going to call ME not mutually exclusive because there is overlap. So just like in the Venn diagrams above, you could represent it like this, okay, where there is one little piece of overlap. That's our 6. Okay. But in the first example, there's no overlap. If you wanted to roll a 2 and a 3, well, it was 2 or 3 and they didn't have any overlap. Right? Okay. You can also represent this with a Venn diagram where here's event A and here's event B, but there is no overlap. Okay. No overlap. Okay. It's another way to consider it. Okay. So hopefully you got all this down. I'm going to be moving on. I'm going to clear my board. Pause the video if you need to take a break real quick. Come back when you're restored.